In this pre-calculus algebra video, we're going to talk about graphing ellipses, and we're going to show how we can derive the equation of an ellipse. So what we're going to do is we're going to take this piece of string over here, and we're going to attach one end, like this end, let's say, to a point over here on the x-axis. So let's say this point is at negative c, 0. So the x-coordinate is negative c. And let's attach the other end right here at a value over here called positive c. So c is some constant. So the left end gets attached there, and the right end gets attached right there. So then what we're going to do is we're going to take the piece of string, and clearly the piece of string is longer than this distance here. So we're just going to stretch it out and hold it taut with a pencil. So maybe it comes to right about there, let's say. So what I'm going to do is I'm going to, remember this end is attached, and I've got my pencil right there, and then the rest of the string goes in that direction, and it's attached here, okay? So basically this loose string has been pulled tight with my pencil right there, and it's attached at those ends. So then what I'm going to do with these points fixed, I'm going to take my pencil and I'm going to move it and keep the string taut the whole time. And when I do that, the curve that's going to be traced out is going to look like this. Okay, so let's go ahead and trace out the curve holding that string taut. Let's do that now. Okay, so what I've obtained is this set of points here. Looks like an oval. It's called an ellipse. Now for a point to be on the ellipse, what has to happen is the distance from the point to that value, to this point right here, when you take that distance and you add it to that distance, you get a constant. Now what's that constant length? In other words, the length of this plus the length of that has to be a constant. That constant is the length of the string, of course, right? Because if you add this length to that length, you get the length of the string. And that's true for any point on the ellipse. Take a point like down here, for example. If you measure the length from the first focus to the second focus, right, if you add those two lengths together, you get the length of the string. So that's how the ellipse is defined. Let's go ahead and write that down now. It's the definition of the ellipse. So let's read our definition of the ellipse. An ellipse is the set of all points in the plane, the sum of whose distances from two fixed points f1 and f2 is a constant. Okay, so this is the ellipse. This is the curve, right? The set of these points is called the ellipse. These are just for illustration. The ellipse is this set of points. It kind of looks like a circle, but it's more oval, right? And the two fixed points are called the focus. So the two fixed points that, let's read it again. The ellipse is a set of all points in the plane, the sum of whose distances from the fixed 2 points, f1 and f2, is a constant. The fixed points are called the foci of the ellipse. So this is the first focus, and this is the second focus, right? And the sum of the distances to those two foci is a constant. So using that definition, we can mathematically derive the equation of the ellipse. Let's go ahead and see how that works now. So here's our ellipse, and here's a point on the ellipse, and here are the foci, right? So here's the first focus, and here's the second one. So what we're saying is that the sum of the distances, that is the sum of this distance and that distance, is a constant. So what does the distance formula say? Well, the distance formula between 2 points in the plane is the square root of x2 take away x1 squared plus y2 take away y1 squared. So remember, to calculate the distance between 2 points, you take the difference of the x-coordinates and you square that, and you add that to the square of the difference of the y-coordinates, and then you take the square root of that. So let's go ahead and apply the distance formula first to this point and that point. So it's going to be x take away negative c. So let's call that, this length, call it d1. So d1 is going to be the square root of x. Now when you subtract negative c, you get x plus c, quantity squared, and then you add it to the difference of the y-coordinates. So y take away 0 is just y squared. And then if we look at the second distance, right, this length, that's going to be, call that d2. That's the square root of, well, x take away c, quantity squared, and we add that to, again, y take away 0 squared, which is just y squared. And then the definition of the ellipse says that the sum of those two distances is a constant. So we want points with coordinates x, y that satisfy the following equation. This distance added to that distance is a constant. So let's write the square root of x plus c squared plus y squared added to the second distance, right? Square root of x take away c squared plus y squared is a constant. Now you can call that constant, you can denote it with any variable you want, but for illustrative purposes, something that's going to be useful for us, let's call it 2 times a, and you'll see why we double it in a moment. So rather than just call this a, I'm calling it 2a, because a is going to have a geometric interpretation in a moment. Now how would you solve this equation, right? We're looking for points that satisfy this equation. So what we're going to do, or what you can do, is you can isolate one radical. So you could get this radical by itself, and then square both sides and eliminate that radical. And you do the same thing for the next radical. In other words, you can eliminate both radicals in this equation, and you'll get the following equation. Algebraically, once you do that, you'll get this, that x squared over a squared plus y squared over a squared take away c squared is equal to 1. Okay, so this equation becomes that when you eliminate the radicals one at a time. So it's going to be helpful for us to make a substitution. So do you see this a squared take away c squared? We're going to replace it with the following expression, b squared. So we're going to call a squared take away c squared, we're going to call it b squared. So this equation, and this is the equation of the ellipse centered at the origin, is x squared over a squared plus y squared over b squared is equal to positive 1. So with this definition, there are a couple things. The first thing is that we created this ellipse. When we wrote this, notice that b squared is obtained by subtracting c squared from a squared. And that shows that a is larger than b, right? They're both positive, but a is going to be larger than b. Now, with that in mind, we have names for the intercepts. So when I look at this curve right here, right, on the x-axis, if y is 0, I'm talking about this point right here or that point right there. So those points are called the vertices. So the vertices are the x-intercepts of the ellipse when the ellipse is elongated horizontally like it is here. So the vertices are positive or negative a, comma 0. So it's the down here you have a squared. So if you look at this equation and y is 0, what do you get? Well, this is gone, and you get x squared over a squared is equal to 1. So x equals positive or negative a. So this point has coordinates a, comma 0, and that point over there has coordinates negative a, comma 0. And likewise, if you were to look for the y-intercepts, that would be when x is 0, right? So when x is 0, you'd have y squared over b squared is 1, so y is positive or negative b. So the y-intercepts would be here, right? So that point has coordinates 0, b, and this point has coordinates 0, negative b. We don't call them the vertices. The vertices are only along the axis that the ellipse is elongated. That axis, so there are two axes, right? Here's the long axis of the ellipse, and here's the shorter one. The long one is called the major axis of the ellipse. So in this case, the way I've written it here, if your vertices are on the x-axis and your foci are along the x-axis as well, your major axis is horizontal. The other axis, in this case though, along the y-axis, is this axis right here is called the minor axis. So your minor axis is vertical. Okay, and one thing that we care about, that we've talked about, is that the foci has coordinates. So these are the foci, right? Here's the first focus, and here's the second focus. And the word foci is the plural of focus. So we have positive or negative c, comma, 0. So those would be the coordinates of the foci. So this is what we need to know for an ellipse centered at the origin, elongated horizontally. Here's the equation of the ellipse, and the vertices are positive, negative a, comma, 0. The major axis is horizontal, the minor axis is vertical, and the foci have coordinates positive or negative c, comma, 0. And don't forget that b squared is defined to be always a squared take away c squared. Now it turns out that you can also write an ellipse. We don't only have ellipses elongated horizontally, they can also be elongated vertically. So when you do that, let's see a picture of that, that's going to look like this. Now what's the difference? Well, the difference is that the foci are always along the major axis, but here I can see that the major axis is vertical. So the major axis is vertical, and the foci, the coordinates are going to be, the x coordinate is going to be 0, and the y coordinate is going to be c. So that point is coordinate 0, c. This point is coordinate 0, comma, negative c. So the foci have coordinates 0, comma, positive or negative c. Now it's still true that the vertices, you still want to denote them with a. Oh, by the way, the equation, I should talk about the equation of this ellipse. To derive the equation, you can do it just like before. You take a point P and you look at the coordinates x, y, and you calculate the distance from the point to the first focus, and you add that to the distance from the point to the second focus, and that's a constant. And when you do that, the difference is that the x and the y have been interchanged in the distance formula. And what you're going to get when you solve the equation involving the two radicals is you're going to find this, that x squared over b squared plus y squared over a squared is equal to 1, where once again, b squared is equal to a squared take away c squared. So do you see how this is different than the previous equation? On the previous equation for the ellipse that was elongated horizontally, it was x squared over a squared. Now it's y squared over a squared. So a is always the larger of the two numbers between a and b. A is always larger than b. If a goes with x, then it's elongated horizontally. If a goes with y, then it's elongated vertically. So with this definition, or with this equation involving a, the foci are 0, positive, negative c, but the vertices, right, up here, that's going to be, because the vertices are always along the major axis, the vertices are going to be 0, comma, a, and down here it's going to be 0, comma, negative a. So the vertices are 0, comma, positive or negative a. Okay, before they were switched for the one elongated horizontally. Okay, so now that we know the equation of ellipses and the definitions of the foci and the vertices, let's go ahead and see how we can find some information about the ellipse given an equation and then graph it. Let's see an example of that. So let's find the vertices, foci, and what's called the eccentricity of the ellipse. And that's the first part. Part B, determine the lengths of the major and minor axes. And part C, sketch a graph of the ellipse. Okay, we haven't yet talked about the eccentricity, and we'll do that as we go. So first of all, here's the equation we're given. And what we first want to do is we want to put it in standard form. Now, if you remember the two forms that we just discussed a moment ago, both of them have a 1 on the right-hand side. Let me go back and show you. So I see that I've got a 1 on the right-hand side here in that equation. And in the previous one, I had a 1 right here. Okay, so that's the first order of business, getting a 1 on the right-hand side. So going back to our problem, so I'm going to get everything involving x and y over to the left-hand side. So it's going to be 2x squared plus 49y squared equals 98. And then I'm going to divide both sides by 98. I'm trying to get a 1 on the right-hand side. And when I do that, I get x squared over 49 plus y squared over 2 is equal to 1. Now remember that when you have it in the standard form, a is not 49. This is a squared, right? Well, actually, even before that, I compare these two numbers, and I see that the larger of the numbers is under x, and that tells me right away that the major axis is horizontal. Right? So we want to know which way it's elongated, and it's elongated horizontally. Now, a is the square root of 49, which is 7. And b is the square root of 2. Right? And then I can find my c as well. Remember that b squared is always defined to be a squared take away c squared. So in this case, b squared is going to, well, sorry, I take that back. Let's go ahead and we have a and b, so let's go ahead and find our c. So if I isolate c squared, I get this, that c squared equals a squared take away b squared. Right? I just added c squared to both sides, subtracted b squared from both sides. And so c squared is a squared, which is 49, take away b squared, which is 2. So I get my c squared is equal to 47. Let's write that, I guess we'll just leave it down here. So we have c squared equals 47. And so c is positive or negative square, sorry, take that back. C is just equal to positive square root of 47. And then, of course, c gives us our foci. So c is the square root of 47. So let's write down what we have. We have our vertices. Now remember, our vertices are positive or negative a comma 0. So our vertices are positive, negative a comma 0, which in this case, it's equal to positive or negative 7 comma 0. And our foci are, remember, those are positive or negative c comma 0. And I know that a and c come first as the x coordinate because I determined my major axis was horizontal. So positive or negative c, it's positive or negative root 47 comma 0. All right. So the one question we're still asked about is this. It's for the first part. It says find the eccentricity. The eccentricity is defined to be c divided by a. And so in this case, it's c is root 47. And a is positive 7. Now, what's the meaning of that? Or what's going to be why is that important? If you look at this definition here, right? This is our definition of b squared. And notice that if c is really large, right? Then if c is very, well, okay, first of all, b squared is always positive. So c squared can only get as large as a squared. So c can't be bigger than the square root of a. So this is capped. C squared is capped at a squared. It can't get larger than a squared. But if c is really, really large, that means this is really, really small, and b would be really, really small. If you had that situation where your b was really, really small, and it was oriented horizontally, what would that mean? Well, remember from our original graph, let's go back to our graph of the ellipse. Right here, right? A is here, and if b is the y-intercept, and it determines the length of the minor axis, if b is really, really small, that would be really, really low like this, and the graph would look like this, right? So when you have what's called a high eccentricity, that means your ellipse has a high amount of curvature, right? It really flattened out. And likewise, let's go back to our equation that we're just working on. Likewise, if c is very small, then b is almost as big as a, and if a and b are very close to being the same size, like right here, right? If a and b are the same size, then you have a circle. So if b gets bigger and bigger, then and a and b are the same, then the ellipse is looking very circular. So eccentricity tells you basically how circular an ellipse is. And the conclusion you draw is this, is that if c is close to 1, sorry, if the eccentricity is close to 1, write that down. If the eccentricity is close to 1, then we have a very curved orbit, or a very curved ellipse. That's the first point. And the second point is this, is that if the eccentricity is close to 0, then it's very circular. It's a very circular ellipse. And remember why that is. Because the only way you get the eccentricity, if this is the eccentricity, c divided by a, the only way that's close to 0 is if c is really small. And if c is really small, that means b is very close to a. And so your x-intercepts and your y-intercepts, they're all sort of the same distance from the origin, and that's a very circular looking ellipse. Okay, so we talked about, so let's box what we have. We have the eccentricity is square root of 47 divided by 7. By the way, this is about equal to, on a calculator, if we type it into a calculator, 0.979. And you can see that's very close to 1, meaning that it's a very curved ellipse. It's very elongated. It's not very circular at all. And then the second thing we were after were the vertices and the foci, which we have here. Okay. Second thing says determine the lengths of the major and minor axis. So let's write this, might as well write it here, that the major axis, right? The major axis, remember if you go back to your graph of the ellipse, let's go ahead and do that for a moment now. So this is the major axis, right? And if that length is a, then clearly the length, that entire length would be 2a. And likewise, the length of the minor axis would be 2b. So the length of the major axis is going to be double 2 times a, so it's going to be 14. And the minor axis, so this is the length of the major axis. I should write MAJ, so you know what we're talking about here. Major axis is of length 14. The minor axis is double the length of b. And what was b? b was root 2. So the minor axis has length 2 times root 2. So that's our answer for part B. Okay, let's go ahead and sketch a graph of this ellipse now. So here's what we have, right? We have, I just, on another piece of paper, I just summarized what we have. Here's the equation of our ellipse. These are the vertices, positive, negative root 7, 0, and the foci are positive, negative root 47, 0, and this is about 6.86, the square root of 47, and the eccentricity is 0.979. Okay, let's go ahead and see a graph of this now. Okay, so here is a graph. Here's a graph of our ellipse. Now the ellipse is in green, and I used it. I graphed this using a program called Desmos on a graphing calculator. And so the purple dots here are the foci. They're not on the ellipse, but they're used to generate the ellipse. So if we zoom in here, well, first of all, I can see that the ellipse goes through the value of 7. But if I come in here and I zoom in, I see that the value is 6.856, and that is those are the coordinates of the foci. And you can see that the curve comes in here, and it goes through 7, but it from a distance it looks like it goes through the focus, but it doesn't, right? Just the focus is very close to the vertices for this ellipse. So this is a very C, in this case C is very large, right? So the eccentricity is 0.979, so it's a highly eccentric ellipse.